Okay, good morning, everyone. So we're going to continue looking at maximums and minimums. And so the last thing we looked at were global maximums and global minimums. And we're going to examine case situations in economics when you worry about optimizing things. So just before we do that, let's just do a kind of little review of what we did last week. Okay. So here we have, we're looking at temperature as a function of time. And so at what time was it the coldest at this place? And what I give you is the derivative at every hour. So what do you think that derivative would have been? So let me ask Elijah here. No. Eric.
It would be 11, wouldn't it?
Exactly. Okay. So again, remember, I'm always going to ask you these kind of like tricky problems, not giving you the quantity, but the derivative. So what is this derivative telling us? The derivative is negative, so that means it's getting colder and colder and colder. It's losing 5 degrees, then it loses 1 degree. Then it doesn't change. Then it loses 2 degrees, then it loses 4 degrees. So you see, we actually predict that 11 a.m. would be something like 12 degrees colder than 7 a.m., roughly. Very good. So that's something I'm going to be checking again and again. It's kind of idea of the difference between a quantity and its rate of change. Okay. Jinu, here is a graph of a crazy function, shown it before. Where is the global maximum of this function? X5? Yeah. Okay, so this one wasn't a tricky one. This was just X5.
X6 and X7 between the I'm not sure. Maybe X8.
No, because X, this is what is the maximum of f of X, and here I give you the function f of X. So what you see is what you get. Okay.
It's FX graph of
So this is the graph of the quantity. So I'm just asking where is the quantity the biggest, and you read that off the graph by just seeing where the highest quantity is. Okay, so it's right here. If this was a graph of a derivative, then sure, it wouldn't be there because all this would be growth, so it'd probably be something like that would be the max. But anyway, no, this is the quantity itself, so it's just asking just for the quantity. Peyton, where is the global minimum?
X9.
Sorry?
X9.
Except there's points over here that are lower.
Okay. So then 3.
Except what's missing?
It's open.
So this has no global minimum. The reason was we would want it to be here, but I deliberately took that point away. So I deliberately took away the minimum. So here is where the lowest values occurs, but at no point does it actually reach that minimum. sort of going there, but never quite makes it.
So X9 wouldn't be right either then?
No, yeah, right. X9 is a local minimum, but it's not the global minimum. Because there's points here that are lower, but at no point does it actually reach that lowest. Matt, here's for you. So here we have a river, and we have two towns. And so they're going to build a pumping station at this point here to pump water both to town 1 and town 2. So they want to put the pumping station at the point where they need less pipe. They want to minimize the distance. Which one of these functions then is going to minimize the length of that pipe?
Would be A.
So which one of these formulas is the only one that gives a distance formula? B, right. This is, distance is given by the Pythagorean formula, right? Because we've got a right angle here and a right angle here. So yeah, B was the only one that actually gives you a distance. So that's there. This, A is kind of a distance, but it just measures zhunk, 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 that distance. So it's not really that useful. Okay. So let's continue looking at max and mins, but let's concentrate on economic situations. Let's put the blank on this. Okay, so in economics, what's the most obvious thing we want to optimize to maximize? Profit. Okay, so we've talked about revenue and cost before, so it's natural to talk about maximizing profit. Okay, so, well, we need formulas. So luckily we know the formula for profit, right? It's just revenue minus cost. So this is an example we go back to again and again and again. Okay, so how can we figure out where the maximized profit is? So there's two ways to do it, right? There's graphically, and there's like an analytic way of using formulas. So graphical way is obvious. You just look at the revenue and cost curves, and you just look where is the greatest distance between revenue and cost. Okay, so let's go ahead and do that. So a typical revenue curve might be something like this. And for a typical cost curve, sorry. So remember, usually we've got fixed costs, so we're going to start above the line here. And what are we going to do? So usually we have kind of at the beginning costs are pretty high, but then we get economies of scale. Oops, I think I've given myself not enough room. Let's put it all there. Right, we get economies of scale, and then at some point we have to build more factories, and so then we go and costs kind of increase like this. So I've given myself enough room. It looks like I have to do it. Okay, and so what we would do would be we would get some kind of scanning thing like a ruler or something like that. And so that profit is a quantity, right? And so quantities are just distances on graphs, right? So we want to see where is the distance the greatest between revenue and cost. Okay, now we're not interested over here, right? Because this is loss. So what do we call this point? That's the break-even point, right? So we would go and we'd say, okay, it's increasing, the profit's increasing. Then after a while, maybe around here, maybe it looks like it could be. Something like that, right? Where if I had a better picture and you had a ruler, I could figure it out pretty straightforward. So graphical analysis is we just see in graph where R is greatest distance. Okay. Let's see what kind of analytic analysis we can do. So we've got a formula. We want to optimize. So what do we know? Okay, we know that to optimize, we want to take derivatives. Okay, so let's take a derivative of this. So we have marginal profit equals marginal revenue minus marginal cost. Set it equal to 0. And what conclusion do we get? When does this equal 0? When they're equal. So when marginal revenue equals marginal cost. Okay, so this is what the model says. Let's think about, does that make sense? Okay, so you've got a factory. Okay, and so when do we, remember we saw this before that like when marginal revenue is greater than marginal cost, what should we do? We should increase production, right? Because marginal revenue is greater than marginal cost, then by putting that extra unit in, we're going to get extra profit. Okay, so we keep on, so like for example, we're here. We see marginal revenue is greater than marginal cost, so we increase production. Marginal revenue is still greater, still greater, still greater, still greater, and we go till when? Till they're equal, because when we reach a point where marginal revenue equals marginal cost, we make no profit on that additional unit. So we stop. We don't increase production. Okay, so what does it it mean for marginal revenue to equal marginal cost? What does that tell us about slopes? They're the same. So basically what we should be doing is we should be looking for when marginal revenue equals marginal cost. This is a straight line, right? So we should just see like here. Here we see marginal cost is parallel to the, there the cost curve is parallel to the revenue curve. And so actually it was here. Okay, and so that's actually, that's just another way to look at it from the graphs as well. So the point at where the distance is the greatest should also be the point at which the graphs are parallel. Should be the same thing. Okay. So here, right, we're taking the derivative. What's the other thing we should always check when we take a derivative and set it to equal to 0? We're going to optimize. So what should we check?
Extrema.
It's an extrema, so we know it's an extrema. So we should check whether it's a min or a max. Okay. So for example, here is another point at which marginal revenue equals marginal cost, but we don't like that one. Why is that? It actually maximizes our loss at this point. This is the worst point. So marginal revenue equals it's the bad extrema. It's the minimum. Whereas this is the extrema we want. So at the same time, just like we did before, we should always kind of analyze our extrema to check that it is a maximum. Okay? And so when is it a maxima? Well, it's a maxima if beforehand marginal revenue was greater than marginal cost, and after marginal revenue is less than marginal cost. Right? Because if beforehand marginal revenue was bigger than marginal cost, that means we're going up, profit's going up. And then afterwards, if marginal revenue is less than marginal cost, that means we're going down. So that's a straightforward maxima. Okay, so all we've done is we're just putting together things that we've done before. We've looked at profit and revenue and cost before. We've looked at maximum and minimum before, and now we're just blending them together and just doing the same thing. Okay, let's sort of continue doing a little bit of graphical analysis. So this is, here we've graphed revenue and cost. So let's graph marginal revenue and marginal cost. Okay, so revenue is a straight line. So what is marginal revenue? It's a straight line. It's a constant line. Okay, so marginal revenue looks something like this. Marginal cost, what do we got? So marginal cost is always positive, but it's not a straight line, right? It starts off high, comes down to a minimum, and then goes high again. So marginal cost is going to look something like this. Now, if I give you this situation, we can recognize where the maximum profit is going to be, right? It's going to be right there. Why? Because marginal cost equals marginal revenue. Beforehand, marginal revenue is greater than marginal cost, and afterwards it's less than. So if we were to then graph profit, what would it look like? It would look like, so what does it look like? So it starts off maybe here. So it goes down, so this would be a minimum. So it would go like that. And then it'd start going up. This point here would be kind of like an inflection point. Here would be the break-even point. And then up here, that corresponds to that, and then it sort of goes down again. And so this is a different way of finding maximal profit, right? This is the profit curve. So maximal profit is just where is the graph the highest. Okay. So notice this, we had 3 different ways of finding a maximal profit, and they're all related. But you just gotta, if you understand how they're related, then that's good, because that means you understand what's happening with derivatives. And if we subtract these 2 things, we get the maximal profit, marginal profit curve. So that's another curve I could have put in there. Okay, so that's how you get at maximum profit by analyzing graphs. Let's do an example with a function. So a much more typical question I would ask would be, okay, let's say Q is between 0 and 1,000. Revenue equals 5Q minus . Okay, so here my revenue curve is a straight line, and then I subtract a little bit, and that's kind of modeling the fact that we're saturating the market and we have to sell our goods for a cheaper price the more we put in. And the cost curve, let's just have it as 300 plus 1.1 Q. So now here I'm modeling cost by, this is the fixed cost, and let's just say in this domain, things just cost me $1.10 to make a unit. So we get a very simple cost curve. Okay, so instead of a graph, now you have a functions, and so now we want to maximize profit. Okay, well, there's nothing to look at, so we have to use derivatives. So marginal revenue is what? Derivative R, so derivative 5Q. 5 minus 0.006Q. Right? And marginal cost is a simple 1.1. Okay, and then to find maximize profit, we're going to check that we're going to find when 1.1 equals 5 minus 0.06 Q. Well, that's straightforward. Bring the 1.1 over there. It's a 3.9. Bring this over here. 6. And so Q is 3.9 divided by 0.006. Anyone got a calculator for me? $6.50. Okay, so it's a maximum problem. So what do we got to check? We've got to check the endpoints, 0 and 1,000, and where the derivative is 0. Okay, so one of these 3 points is going to be where we're minimizing profit, and one of these points is where we're maximizing profit. So let's just go ahead. When Q is 0, it's minus 300, right? Because no revenue and we outlaid $300 in cost. When Q is 1,000, this is what? 5,000 minus minus 3,000, is it? That's 2,000 revenue, and 1,000 times that is 40. So I think it's something like 600. And then we plug in 650. Can someone help me out here? I've got a calculator up here. Can someone figure out the revenue? So Eric, can you figure out the revenue for 650? And I'll try and figure out the cost of 650. 715 equals 1,015. I should have been a calculator class.
I got 1,982.5.
1,982.5.
82.9.
I subtract one from the other, and it looks like I get something like 967.5. Okay, so that's where we should put our factory at. We should be producing 650 units. Okay, so we started off by just doing purely graphical stuff, just looking at graphs and just seeing where things are the biggest and where slopes are the same. And then analytic, we come up with formulas and we solve the formulas and we come up with the answers that way. Okay. Let's have a look at it. We're section 4.4. So we've done a graphical problem, we've done a formula problem. What's the one type of problem we haven't done? Table, right. So a numerical problem. And that's not going to be so hard. This is a problem from the book, problem number. Okay. So table problems can come in two flavors, right? One where you're given values of revenue and cost, and there you just look for where is the revenue, the biggest difference between revenue and cost. Or I could give you marginal revenues, and now you're looking for where marginal revenue equals marginal cost. Let's say 5,000, 6,000. Okay, and marginal revenue. Okay, I did a lot of writing for a very simple problem. Where do we maximize profit?
8,000.
Yep, that was the simplest problem of all. Marginal revenue equals marginal cost. We see beforehand marginal revenue above marginal cost. Afterwards, marginal cost above marginal revenue. So it is a maximum. So you gotta check that. But there we go. That's it. So as long as you understand, right, when it's derivatives, you want equality. When it's the revenue and cost themselves, it's like when is one bigger than the other. So that's just all about understanding the difference between a quantity and a rate of change. Okay. What other kind of things would you want to maximize? When would you want to maximize revenue?
There's no cost.
Hmm?
And there's no cost.
Or fixed costs, right? So in some businesses, you've got your costs, and like for example, you run a bus company, and you're running a bus, and you go every hour between two towns, and this is where you're at, and so obviously the difference between 20 customers and 21 customers is not going to give you any extra costs. At some point, it is going to give you extra costs, right? Because you have to get an extra bus and extra shifts or whatever. But typically, if you're kind of running a business like that, or you have a movie theater or something like that, in some situations, your costs are kind of fixed, and so really, the thing that you're focused on is maximizing revenue. So let's have a problem from that. So let's say you run a bus company, and you know that when the price is $80, you get 300 customers. Let's say, there's 300 customers per day when you do your big schedule, whatever. And you notice that each time you cut price by $5, you get an additional 30 customers. So the question is, what price maximizes revenue? Okay, does this kind of make sense? Okay, so this is a different kind of problem from before. Before we were varying output. We've got a factory, we're making some good, and we're varying our output, and we're trying to find the sweet spot here. Costs are fixed. So what information does these two things give us? What it's telling us something about the customers. What information is it giving about the customers?
It's kind of like the marginal amount. 'Cause
It
it's-
is. I mean, this is kind of marginal amount, but what do we call this thing? Like, what do we call what customers want? Demand, right? So this is giving us a demand curve, right? Okay, so let's think about revenue. So the thing is, we want to do some analysis of revenue, so we've got to find a formula for revenue. Okay, so revenue, what's the formula for revenue? Price times quantity, right? And in this case here, the quantity is the demand, right? Because we're just offering the service. And so the quantity that's actually going to turn up is going to be the quantity demanded. So the first thing we've got to figure out is the demand curve. What can you tell me about the demand curve? The fact that every time we cut $5, we get an extra 30 customers. That means that the rate of change is constant. So what kind of curve do we have? It's a straight line. Yeah. So that's good. We know for a straight line, all we need is 1 point. Right? So when price is 80, we get 300. That's a point. And we need the slope. And the slope tells us what? We cut the price by $5. You get an extra 30 customers. Right? Slope is just rise over run. Okay, we've got a point and a slope, so we can write that down, right? So what is it going to be? It's going to be Q minus 300 equals price minus 80, and then the slope is minus 6. So we just fit it into the equation. And now we should just solve for Q, right? Because we want to put it into here. So Q equals minus 6P plus 480 plus 300 equals minus 6P plus 780. And let's just double check. When P is 80, we get minus 480 plus 780 is 300. Okay, it works. And so now our revenue equals price times 780 minus 6. It is 780p minus 6p squared. do we maximize that? Sorry?
But you said equal to 0, then fine.
Well, now that's when revenue equals 0. What do we want to be 0? If we're going to optimize revenue, what has to be 0?
The difference is
Revenue derivative, right? Marginal revenue has to be 0 because marginal revenue means we're getting extra money from that extra thing. So we take the derivative, 780 minus 12p, set that equal to 0. So we want to do p is 780 divided by 12. What's that? 6, isn't it? 65. So we should set our price at $65. Right, we're getting less money per customer, but it's the sweet spot for multiplying customers by money. Okay, that kind of all making sense? Okay, so all we're doing is just applying what we've done before to kind of these kind of situations. It was too much. So, this is what we've been doing. Okay. So we've been starting out by looking at cost and revenue. And so the straightforward way is when we're just dealing with quantities is just by looking at the biggest difference when the R is above C. So here we get the situation here. So here we see the maximum profit is 20. That's the biggest gap between C and R. So we already did that one. So the thing we saw that by looking at derivatives, we see that this point here where the maximum difference is, you can kind of see that these curves here are parallel, right? So here, marginal revenue equals marginal cost. So that's kind of what we kind of emphasized upon. Okay. So in which one of these situations, how can we increase profit by increasing production? So we've seen this before. In which one of these scenarios are we going to make more profit if we increase production? B, that's the maximum. Okay, so at the maximum we should do nothing. We should, and we're at the maximum, we're happy, we shouldn't do anything. I'm saying, when should we increase production? A, right? Because if marginal revenue is marginal revenue is greater than marginal cost, then it helps us if we increase production. If we're at C, if marginal revenue minus marginal cost is negative, then we should cut back, because that will optimize things. D is kind of like a red herring. Okay, so that's that section then.